So finally, you know, in quantum physics, we have the transmission probability of alpha particle of energy E across a rectangular potential barrier. Be careful, we are calculating now for a potential rectangular potential barrier. We don't talk about a exponential barrier. So we have a rectangular barrier with a height u and width equals to L. The transmission probability Pt equals to exponential minus 2 k2L. You know k2 is a wave number inside the barrier calculated before, which is equal to radical to m u minus e divided by h square. We can substitute the value of q of k2 here to get finally pt equals to exponential minus 2 times radical to m u minus e divided by h square times L. You know, here we have the alpha particle inside the nucleus. And at the edge here, we have a rectangular potential well. Excuse me, a rectangular potential barrier. Okay. Inside the nucleus, alpha particle will have many collision with the inside wall of the nucleus. Okay. And it tries to come out of the nucleus. So PT for PT is the probability of tunneling for each attempt. What I mean, for each attempt, we have a certain probability to get out of the nucleus. PT is the probability of tunneling for each attempt. If we have 100 attempts, so we have 100 PT. Okay? Okay, now uh, we go to the second term, the decay probability per unit time, lambda. You know, lambda, it's called decay rate or decay constant or the decay probability per unit time. You know, in unit time, for each unit time, for example, 1 second, 2 seconds, alpha particle will hit the surface several times. Okay, so here we have a probability of tunneling per unit time. It's lambda. So lambda equals to f times pt. You know, f is a number of attempts per unit time, and pt is a transmission probability of tunneling per attempt. Okay, for example, here we have one attempt and we have pt. In 1 second we have a many times of attempts, okay, or many attempts. In this case we can talk about lambda to count these attempts per unit time. So lambda equals to f times pt, and you know we have a relation between lifetime t half and lambda. You know t half equals to len 2 divided by lambda. Okay, so now we calculated, we said lambda equals to f times pt, and we have pt which is equal to exponential minus 2 k2L. Let's say we have an alpha particle inside the nucleus, and for each collision we have a certain probability pt. Between two attempts, okay, for example, uh, between this point and this point, we have a distance of 2r0. is the radius, nuclear radius. Okay, and alpha particle will take a time t to pass from this point to this point. So you know the distance equals to that equals to v velocity times time. Here v small v. We can say small v. Okay, so we can say the distance equals v times t. So you know in this case the collision frequency f equals to 1 over t, which is equal to the velocity divided by 2 r0. You know the unit of f is second minus 1. Okay, and for example, if we have the velocity, it's about 2 times 10 power 7 m per second. We have the radius uh, of the nucleus equals to 10 power minus 14 m. So we get f equals to 10 power 21 at 21 collision per second. Okay, so f is the number of attempts per second, the number of collisions per second, f. Okay, so as we have here lambda equals to f times pt, we can put here f by its value, which is equal to v small v. Okay, we have v velocity divided by 2r0 times pt. Okay, okay, now here I repeat the same page. Okay, look, here we calculated pt equals to exponential minus 2 radical k2, which is equal to radical 2m u minus e divided by h square times l. You know, now we have to explain, we have to go to the real case where we have an exponential decreasing of the potential barrier. Okay, this expression of pt is for the rectangular potential barrier where u, you know, the height u is constant, and then the wave number k2 is constant. So in this case we have a constant pt in the case of a rectangular barrier. But in our case, in the case of here, we have a barrier of varying height. So u and k2 are not constant. We can say k2 equals to radical 2mv in function of r, because as you see here, the value of v will decrease. We can say here we have the potential barrier, and from here to here, v will decrease. So for each value of r, we have a value of v. So u will be in function of r or v minus e divided by h square. Then pt must be modified. We have to modify this pt to have to apply pt on our case. Okay, we come back. You know, here this equation is applied only in the case of a rectangular shape. But in this case, in our case, we don't have a rectangular shape. In order to have this shape, we can minimize and we can divide the shape to a small rectangular shape. As you see, we have a small rectangular, many one we can put, okay? So we can calculate the PT for the small potential barrier, for the small one, for each one, and we do the integration to cover all the potential barrier, okay? So how can we do it? We can say PT equals to exponential minus 2 K2L. We can take a natural logarithm, ln PT equals to minus 2 K2L. Okay? This equation is changed to integral form. I want to integrate this equation from the small portion to cover all the potential barrier. Okay? So we can put ln pt, which is equal to minus 2 integral, because k2 is not constant, so we have to do the integral between, let's say here we have you know initially like this, okay, between 0 and L we have a length equals to L. So we can put between 0 and L K2R dr, and we can put it between R0 and R, okay? Between this point and this point. Okay. So we can put the limit of this integral between this point and this point. K2R, the variable term, times dr. dr is a small portion. If you look well here, is the distance from here to here. This is dr. Okay. We have to integrate from this point to this point. So this one has a dr thickness. It means in the place of L, the total L, we put dr simply. So R is the distance, you know here, R, this point, is the distance where we can calculate V. We calculated before. You know V at this point, which is equal to 2ZE square divided by 4 pi epsilon 0 R. Okay, here what I am doing, I want to calculate the value of PT. Just to explain the situation, I want to calculate PT. After the calculation of PT, I want to calculate lambda. This is the main point here. Okay, so we go step by step. We have a lot of calculation. You have to understand all the steps. First of all, V at this point, you know, we have the equation of this curve, which is equal to 2Z E square divided by 4 pi epsilon 0 R. Okay, so V, we can put here capital R for this point. The energy of alpha particle at this point, you know, at this point equals to the energy of the potential barrier at the point where alpha particle is coming out the nucleus. Okay. You know, now I want to calculate K2R. You know, K2 is not constant because we have a variable VR. Will change with the distance. Here I separate this equation. I can take 2m divided by h squared out, and here we have this term and this term power half. Here I substitute the value of VR here to get this term. Okay, you know, E of alpha particle, we have alpha particle here with a constant energy. I said this before. The energy of alpha particle, before the potential barrier is equal to the same value after the potential barrier. So alpha here is constant, so it can be calculated at this point, where the energy of alpha particle, E, is equal to the potential energy, V, at this point, VR. Okay? We calculated before, VR equals to E at this point. So here we can say E equals to V capital R equals to this value, where E is constant. Here I substitute the value of E here, it's okay. And what I did at this point, I can multiply by capital R, and here I divide by capital R. 2z e square, 2z e square divided by 4 pi epsilon 0 times R equals to E. And we have here capital R divided by small r, it's here. Okay, minus this one equals to E. So here we have E and E. Power half, we can take a common factor and put it inside here. Why? This term is constant. I put all the constant parameters together. So here we can put 2m divided by h squared E power half equals times R capital divided by small r minus 1 power half. Here, at this point, we have K2 calculated before. Just I substitute the value of K2 in the initial equation, this one. Okay. You know, we have K2. Here, we can put this term out of the integral because it's constant. And it's inside we have this one. Let me look here. We have a pure mathematical calculation. Okay, you know, to solve this integral, we can take small r divided by capital R equals to cosine square phi. So R equals to capital R cosine square phi, and dr divided by d phi, which is equal to 2r cosine phi times minus sine phi. So we can calculate dr, which is equal to minus 2r cosine phi sine phi. Okay, this is the value of dr. We can put its value here to get finally this term. Okay, we can substitute here. You know, here we have capital R divided by small r. Capital R divided by small r equals to 1 over cosine square phi. Okay, we substitute the value of this one by 1 divided by cosine square phi, and we put dr here, we get this answer. Okay, now we have this value is calculated before. Let me, you know, one moment. So, you know, 1 over cosine square phi equals to secant square phi minus 1 power half 2r cosine phi sine phi d phi. Secant square phi minus 1 equals to tangent square phi. Okay, and we write the equation. You know here, let me see. Here we have tangent square phi power half, okay, like x squared, we get x, okay? So we have minus tangent phi, we get out of half, and we put the rest. You know, we have tangent phi, which is equal to sine phi divided by cosine phi, and here we have cosine phi, sine phi. We can eliminate. We have, let me see, we have minus sine phi divided by cosine phi times 2r cosine phi sine phi. We can eliminate cosine with cosine. We have finally sine phi square. Okay, so we have minus 2r sine phi square d phi. And you know, sine phi square equals to 1 minus cosine 2 phi divided by 2. Okay, and we can eliminate 2 and 2 to get minus r, 1 minus cosine 2 phi d phi. So here we come back to the equation, integral of r divided by small r minus 1 half dr, which is equal to minus r 1 minus cosine 2 phi d phi. Okay, I am calculating the integral now. You know, the integral of d phi equals to phi. The integral of cosine 2 phi equals to half sine 2 phi between the limit between r0 and r. Okay, you know how you can do it. We come back here. We arrived to this point. Here, let me see. We have before. Okay, we have minus r sine 2 phi. Okay, you know sine 2 phi equals to 2 sine phi cosine phi. Okay, sine 2 phi equals to 2 sine phi cosine phi divided by 2. We can eliminate 2 and 2 to get finally this one. Now we come back to the assumption r small divided by capital R equals to cosine phi square or cosine square phi. So I want to put phi by its value, sine phi and cosine phi. So here the main point is to calculate each term in function of small r and capital R. Okay. First of all, we have to calculate phi. We can start from by this one. Phi equals to cosine minus 1 r divided by capital R half. You know, we have cosine, we can say cosine square phi equals to r divided by capital R. So cosine phi equals to radical r divided by capital R. We can say phi equals to cosine minus 1 of r divided by capital R. Okay, so we can put phi by its value. It's okay. We calculated phi. Now cosine phi also can be calculated, which is equal from this one to r divided by r half. And also we can calculate sine phi. Okay, you know, sine phi square plus cosine phi square equals to 1. So sine square phi equals to 1 minus cosine square phi equals to 1 minus r divided by capital R. Okay. Now we substitute the value of each one. Here we have integral. Okay. We have this one. I put phi by its value and sine phi and cosine phi. Okay. Here, just I want to simplify. You know, here we have the limit. We can solve it. Okay, you can do it easily. Just you put small r by capital R minus R0. Okay, if you solve it, you arrive to this one. So, okay. Now, you know, in the real case, we have a large potential barrier. In general, you can say the real case, we have a small radius of nucleus and we have a large potential barrier. If we have here the value of R and here we have the value of R0. So R is very big in terms of R0. We can do this approximation. In this case, let me simplify the situation. Before I want to calculate each term, let me start with this one. This one, we have a very large R. It means this one equal to 0, 1 minus 0, exponential, voila. Finally, we have 1, this term. This one equals to 1. I want to solve this one. First of all, let me come back to review this point. Cosine theta in general equals to sine 90 minus theta. Okay? If theta is small, so sine 90 minus theta equals to 90 minus theta. So cosine theta equals to 90 minus theta. We can say cosine theta equals to 90 minus theta if theta is small. Okay, because in this case, what we have here, here we have cosine. In this case, we have cosine minus 1 R0 divided by capital R half. We can say equals to 90 equals to pi over 2 minus theta. Theta equals to R0 divided by capital R half. Okay? So we can substitute this value here. And this one equals to 1. And we can put this one also by its value. Okay? Doesn't change. Anyway, we come back to the equation. We put here the value of the first one, 1 for the second one, and here we have R0 divided by capital R power half. Okay, finally, we arrive to this relation of len PT, transmission probability. Okay, at this point, we have this one. Here, just I want to simplify. We have pi over 2, and here we have minus, we can say, we have the same value here. This one equals to this one. So we have minus 2 R0 divided by R power half. Okay? Here, you know, R can be calculated. We have E as a constant value equal to ZE squared divided by 4 pi epsilon 0 E, capital R. Okay? We can calculate R from this equation. We get here. And at this point, we substitute the value of R here and here. Okay? We simplify the equation. Just if you put its value here and you eliminate the same parameter, you get the answer. We continue. Here we have minus 2 to m divided by h square e power half. R equals to, I put it here. Okay, pi over 2 minus 2 R0, it's here. And we put divided by capital R, which is equal to 2z e squared. And here we have 4 pi epsilon 0 e. Okay, simple. Here we can simplify this term times this one, and this one, the total one. Okay, the total times this one, and the total times the second term. We arrive finally to this equation. If you put this term and you simplify, you can get this final equation of len PT. Okay, you know, 4e divided by h times m divided by pi epsilon 0 power half equals to 2.97. And epsilon is e squared divided by h epsilon 0 m divided by 2 power half equals to 3.95. Just we substitute these values here. We get finally here len PT equals to 3.97 Z half R0 half minus 3.95 Z e power minus half. You know Z, when we have VR equals to, initially we have Z minus 2 times E times 2 E divided by 4 pi epsilon 0 R. We put Z minus E is the atomic number of the daughter nucleus. We can put it Z, okay, just to simplify. Okay, so Z is the atomic number of the daughter nucleus. E is the energy of alpha particle. So it's a very important equation. We can calculate the probability of transmission. If you know the value of E, it's easy to calculate it. By a sample detector, we can calculate the energy of alpha particle. We can have the value of the radius of any nucleus. We can know the Z proton of any atom. So it's easy to calculate the coefficient of transmission, PT. So now we have the value of PT. Very important. Now, if you know PT, we can calculate lambda. You know lambda equals to the velocity divided by 2r0 times PT. To calculate len PT, we put len lambda equals to len of the first one plus len PT. Okay, simply we put len PT by its value here. We get len lambda equals to len V divided by 2r0 plus the value of len PT. Here in function of len lambda, you can use it, or you can put it in function of len or log 10. You know, len equals to len E. Yes, now I want to put it in function of log 10 lambda. You can put it like this or like this. In the next slide, I will compare, if we have time, I will compare this theoretical result with an experimental result with a curve. You can see uh, the um, the difference between them if we have a coincidence between the theoretical simulation result and the applicable or the applied result by experience.